We're going to solve a really interesting problem called the Basel problem, which is this. What is the sum from n equals 1 to infinity of 1 over n squared? This is a problem that mathematicians wondered for a while, and it was solved by Euler using some facts that at the time weren't proven, although it ultimately gave the right answer, and then the facts that he assumed were true were then proven later. Now, there's plenty of proofs on YouTube of the Basel problem using those facts. It involves taking an infinite factorization of sine x divided by x, and then comparing it to its Taylor series, comparing coefficients, and then you solve the problem. However, it requires a proof of something called the Weierstrass factorization theorem, which is something I personally do not understand the proof of. So I didn't feel exactly comfortable delivering a proof of the Basel problem using that fact when I don't actually know where that fact came from. This, on the other hand, is a proof that uses just calculus and algebra, and it's pretty self-contained, so I think it's a really great proof for someone who wants to see why this sum equals pi squared on 6, but they don't exactly have the most complicated mathematical machinery at hand. Right, so let's get right into it. First, we want to show that cotangent theta plus I to the 2n plus 1 power minus cotangent theta minus I to the 2n plus 1 power divided by 2i equals sine of 2n plus 1 theta divided by sine of 2n to the 2n plus 1 power, okay? Note here, n is natural and sine theta does not equal 0, because if sine theta equaled 0, catastrophe would occur because we'd have a division by 0, okay? Now, to show this fact, right, we're going to use something called De Moivre's theorem, which is a pretty standard theorem in complex numbers. And it essentially states the following: cosine theta plus I sine theta to the nth power equals cosine of n theta plus I sine of n theta. And although this is really nice algebraically, it just looks like you're taking the power and chucking it down into the argument of the trigonometric functions. What it means geometrically is that if you have a complex number as a point in the complex plane, then raising it to a power, say 3, is the same as just rotating it by the complex number's argument 3 times. But this is something for another video, De Moivre's theorem. I'm going to abbreviate De Moivre's theorem as DMT because I'm just going to butcher the pronunciation of it, okay? So without further ado, let's jump into it, right? Cotangent theta plus I equals, well, cotangent theta is nothing but cosine theta divided by sine theta. It's the reciprocal of tan theta, right? So it's going to be cosine theta over sine theta. And I is the same as I sine theta divided by sine theta, right? Because we want to bring them to a common denominator. So we get the following, okay? And now we're going to raise both sides to the 2n plus 1 power. Board's a bit shaky. Right, but raising a fraction to the 2n plus 1 power is the same as raising the numerator to the power and raising the denominator to the power. Okay, so we're going to do precisely that. Okay? Hold on. I think I could get this. Yes, brilliant. Okay, so we see here that we get cosine theta plus I sine theta to a natural power is 2n plus 1. So we can apply De Moivre's theorem. And this gives us the following. And then the bottom just stays sine to the 2n plus 1 theta, right? And this is looking really good, right? We've shown that cotangent theta plus I to the 2n plus 1 power equals this bad boy. And that includes a sine term with an argument of 2n plus 1 theta, which is great because our goal is exactly something looking like that, okay? Now, before we go into cotangent theta minus I, right, let's think about DMT for a second, right? DMT holds for all angles theta, right? So we can let theta equal negative theta, right? If you find that confusing, we could just let it equal negative x, right? But essentially, we're going to chuck in a negative argument to these trig functions and see what happens, right? So letting theta equal negative theta for DMT, right? Well, cosine of negative theta is just cosine theta because it's an even valued function, okay? And then sine of negative theta is going to be negative sine of theta because it's an odd valued function. To the 2n plus 1. And similarly, cosine of negative n theta is going to be cosine of n theta, and sine of negative n theta is going to be negative sine of n theta due to the even and odd natures of these functions, okay? And this is a pretty standard thing to do, letting theta equal negative theta. We use it in Euler's formula as well when we're trying to find the complex definitions of sine and cosine, right? Sorry, the power here should be n, not 2n plus 1, right? So it's just an alternative form of DMT where we have a subtraction rather than an addition, okay? So let's remember that. We basically just flip the sign. So cotangent theta minus I, when brought to a common denominator, is going to be cosine theta minus I sine theta over sine theta. And then raising both sides to the 2n plus 1 power, right, is going to be the following. And then applying the alternate version of DMT is going to give cosine 2n plus 1 theta minus I sine 2n plus 1 theta divided by sine of 2n plus 1 theta, okay? And once again, this is looking really, really good because we've got two things, cotangent theta plus I to the 2n plus 1 and cotangent theta minus I to the 2n plus 1, and we're about to take their difference. And we can see that when we take their difference, the cosines are going to cancel out, and the sines, due to the double negative that's going to occur, they're going to double up, right? And we're going to get something which looks awfully similar to this, okay? So I'm just going to wipe the board up and then we'll continue with the next part. Okay, so now we can see we're going to take the difference of these two terms, right? And because they had the same denominator, I take the liberty of bringing them to a common denominator, okay? So we have, we can see this numerator, the cosine 2n plus 1 theta terms are going to cancel, right? And the I sine 2n plus 1 theta terms are going to double up because of this double negative turning to a positive. So we get 2i sine 2n plus 1 theta over sine just 2n plus 1 theta, okay? So we can see that the difference of these terms equals this. And if we divide by 2i on both sides, because it's essentially an equation, we get precisely this statement, right? So that's us achieved our first goal. Okay, I'll wipe up the board and we'll go to the second part. So the next part is, we want to show that the solutions of the above polynomial, right, are x equals cotangent squared of m pi divided by 2n plus 1, where m ranges from 1 to n, okay? How on earth are we going to do this, right? Well, first of all, we can see that there's like a 2n plus 1 here and a 2n plus 1 there, and we're talking about solutions of polynomials and like just roots in general. So why don't we consider this the right-hand side of our identity and find the solutions to it, right? So consider sine 2n plus 1 theta divided by sine to 2n plus 1 power theta, and that equals 0, okay? Now recall, sine theta doesn't equal 0, so this denominator doesn't equal 0, so we're all good. Well, we can multiply both sides of the equation by sine 2n plus 1, and multiplying by 0 is just going to annihilate it, and the denominator disappears, right? So we now have the equation sine of 2n plus 1 theta equals 0, okay? So this means 2n plus 1 theta needs to equal, right, m pi, right? Where m goes from negative n to negative 1, 0, all the way to m, okay? It's going to have two n plus 1 solutions. Sorry, there should be an n. It's going to have two n plus 1 solutions. However, We assume sine theta doesn't equal 0. Sine theta would equal 0 if m was equal to 0, yes. So we need to remove this solution, okay? So now there's two n solutions, okay, to this, before they start to repeat due to the cyclical nature of sine, okay? So for this to be 0, 2n plus 1 theta needs to equal m pi, where m is negative n to n, excluding m equals 0, because that would make sine theta equal 0, okay? And then dividing, we get theta equals m pi divided by 2n plus 1, where n is the following values. And this is looking really good because that's the argument of this thing. But m is currently going from negative n to n, whereas this m only goes from 1 to n, right? But we'll work that out in time, okay? So we're going to pause there for now, and now we're going to consider a different way of expressing the left-hand side, okay? Okay, so now we're going to look at an alternative way of expressing the left-hand side of the identity we showed at the start. So, first of all, remember what the goal is. The goal is we're going to solve this polynomial where the coefficients have the n choose r function in them. Where does the n choose r function show up? It typically shows up in the binomial theorem. And right enough, we have binomial expressions here, right? So you should really feel the binomial theorem just asking to get used, right? And that's precisely what we're going to do. So cotangent theta plus I to the 2n plus 1, just using the binomial theorem, well, it goes from k equals 0 to the power, so 2n plus 1, of 2n plus 1 choose k, times cotangent to the 2n plus 1 minus k power, times I to the k power. Okay. And for now, I'm going to split this up into terms where k is odd and terms where k is even. This is a finite sum, so this is totally justified and allowed to do. So we just have the exact same sum, but we've split it into its odd and even components, okay? And now for cotangent theta minus I, right, we're going to get the same thing, except we're going to have negative I to the k, right? Which is the same as negative 1 to the k times I to the k, okay? Now, we're going to have a negative 1 to the k power. That's the only difference between this expression and this expression. When negative 1 is raised to an odd power, we're going to get negative terms. And when we have negative 1 to an even power, we're going to get positive terms, right? So if we split this straight away into even and odd components, let's see what occurs, right? Sorry for the shaky board. So we can see here, the even valued terms, as I said, we have a negative 1 to the k power, but k is even, so this is just going to equal 1, and in the multiplication, it's going to be irrelevant, okay? Whereas in the odd ones, we're going to have negative 1 to an odd power, so we're going to get a negative number, so we can pull the negative out and have it here, okay? Okay, so splitting cotangent theta minus I to the 2n plus 1 using the binomial theorem into its even and odd components, we get a very similar looking object, except we have a negative version of all the odd terms, okay? So this means that their difference is going to be something very interesting, right? The difference, well, the even summations are going to cancel out, aren't they, right? And the odd summations, well, there's a double negative, right? We have this minus this, so we have two lots of all the terms where k is odd. Okay? And you've probably been wondering to now, why have I just been saying odd k rather than like actually explicitly showing how we're going to index over odd values? So we're going to do precisely that. We're going to do an index shift, right? So we want only odd k values, right? Well, if k ranges from 0 to n, and whenever we want an odd number, we'll do 2k plus 1, right? This is because if you have a number k, and you get it, and then you turn it into 2k plus 1, you're always going to get the kth odd number, okay? So essentially we're just applying that that like index shift or that transformation to k. Okay, can we see this? Yes. So this becomes 2 lots of k going from 0 to n of 2n plus 1, 2k plus 1, cotangent. Okay, so we're going to have a cotangent 2n plus 1 minus we're going to have this, okay? I'm now going to wipe the board so I can bring it up here and we have a bit more space to work with, okay? Okay, so I've cleaned up the board a little bit and we see that the difference of these two expressions is 2 times this summation. Notice k is now going from 0 to n, but every instance of k in the expression has become 2k plus 1 because we're now going to just loop over the odd, only odd k values, okay? So let's rejig this a wee bit, right? We have 2n plus 1 minus 2k plus 1, right? This becomes 2 times n minus k, okay? And this I is I to the 2k plus 1, which is the same as I to the 2k times I, right? And now I is just a constant, so we can pull it out of the summation. We have this. And furthermore, I to the 2k is the same as I squared to the k. I squared is -1, and -1 to the k, we'll write that now, and we'll see, that -1 to the k is going to be positive for even valued k terms and negative for odd valued k terms, as I said before. So really interesting, this is an alternating series, okay? And therefore, if we divide by 2i, we're going to get that the left-hand side of this identity equals this summation, okay? So we're almost done. Before we showed that this left-hand side is actually equal to this summation, right? By taking advantage of the binomial theorem. Okay, but let's expand this summation out, right? It's 2n plus 1 choose 1 of cotangent squared theta to the nth power minus 2n plus 1 choose 3 of cotangent squared theta to the n minus 1 power plus etc. all the way to -1 to the n. It's an alternating series. And you can verify that this definitely expands to that. Now, this looks so incredibly similar to this polynomial up here, except instead of cotangent squared theta, we have x, right? But before we do this, let's take a little note, okay? The right-hand side had roots of theta equaling m pi divided by 2n plus 1. Let me write this down in fact, right? This right-hand side had roots m pi divided by 2n plus 1, where m goes from -n to -1, and then 1 to n, okay? So because this gives roots to the right-hand side, it also gives roots to the left-hand side. So actually, this expression has roots whenever theta equals m pi divided by 2n plus 1. I hope that makes sense, right? The right-hand side, we found the roots for because it's very easy to find the roots for the right-hand side. The left-hand side, not so much. But because we proved they were equal, they must share the same roots, right? So now let's let x equal cotangent squared theta, okay? And we get precisely and we get precisely the polynomial that we're trying to find the roots for, okay? So when does this have roots? Well, remember, this has roots whenever theta equals n pi on 2n plus 1, right? So it has roots whenever x equals cotangent squared of that theta value, n pi on 2n plus 1, right? So we've basically shown this. However, there's one small caveat, right? Here it said m ranges from 1 to n, whereas here it says m ranges from negative n to negative 1 and 1 to n, right? We seem to have double the solutions, which doesn't seem to make sense because we have an n degree polynomial. So by the fundamental theorem of algebra, we should only have at most n roots. The thing is, when we plug in, say, a negative n value into this cotangent squared, because cotangent is an odd valued function, we can take the negative out. So we're going to have negative cotangent of this thing, but then we're squaring it. And because we're squaring a negative number times this cotangent, we just get the cotangent. The negative goes away due to the squaring. So we actually lose all the negative values, and therefore m only really ranges from 1 to n. Okay? And that basically solves this part of the problem. So just to reiterate, because I believe this is the crux of the proof, we find the roots to the right hand side, and they're of the form theta equals n pi divided by 2n plus 1, where m ranges from negative n to negative 1, 1 to n, excluding m equals 0. We then considered the left hand side and applied the binomial theorem to the two binomials in the numerator, and we find that the left hand side is equal to this alternating series. Okay? We expand it and we see it's incredibly similar to the polynomial up here, except that cotangent squared should be replaced with x. We make that substitution, and once again we notice, because we have the roots to the right hand side, and it's equal to the left hand side, then it must also be the roots to the left hand side. So this has roots when theta equals n pi on 2n plus 1. So if we let x go in place of cotangent squared, then it has roots whenever x equals cotangent squared of n pi divided by 2n plus 1. And due to the squaring of the cotangent, we lose all the negative m values because cotangent is an odd valued function. So there we go. We've now found the roots to this polynomial, and we can go to the next part of the proof. Okay, it should be pretty smooth sailing from now on. So we want to now show that the sum from m equals 1 to n of cotangent squared of m pi divided by 2n plus 1 equals the closed form n times 2n minus 1 divided by 3. That's really nice. So let's prove it. And for brevity, we're going to say that c sub m is equal to cotangent squared of m pi divided by 2n plus 1, just to save me writing it out all the time. So this polynomial up here equals 0, and has roots of cm, where m goes from 1 to n, okay? We showed that in the previous part. We know that if a polynomial has roots, then we can factorize it using those roots. That's called the factorization theorem, okay? So this polynomial can be expressed as the following: a times x minus c1, x minus c2, all the way to x minus cn. This is just the product of the n roots we found, okay? Now, what's the leading coefficient? Well, the leading coefficient is going to be a times x to the n, right? So it ought to match the coefficient of the x to the n term, which is 2n plus 1, choose 1. How many ways is there to choose one object from a collection of 2n plus 1 objects? There's precisely 2n plus 1 ways, right? So a turns out to be 2n plus 1, okay? Now, this is a big, long factorization. We're going to want to match coefficients, right? And we see that 2n plus 1 choose 3 looks like it's probably going to give us the closest to this possible. So why don't we consider matching the x to the n minus 1 coefficients, okay? To get all the x to the n minus 1 terms, right, we basically select x from n minus 1 brackets, and then we select negative ci from the remaining bracket, okay? That's because whenever we distribute amongst a product, essentially we're just choosing either A or B from each binomial in the product, okay? So to get all the x to the n minus 1 terms, we're going to select n minus 1 x's, and then we're going to get a negative ci term in the final bracket, and that's going to give us the x to the n minus 1 terms, okay? So the x to the n minus 1 terms are going to be the following. Well, it's going to be 2n plus 1 times negative c1 x to the n minus 1 minus c2 x to the n minus 1 minus all the way to cn x to the n minus 1, okay? And now this thing is equal to x to the n minus 1 times 2n plus 1, and then I'm going to factor out a negative, and then we see that if we factor out the negative, we're just adding up c1 through cn, which is the sum, right, we were looking for up here. So this is looking very good. So we now have two different ways of expressing the x to the n minus 1 term. Up here, we have it negative 2n plus 1 choose 3, but down here, the coefficient of the x to the n minus 1 term is negative 2n plus 1, the sum of the cm's. Let's match them and let's get an expression, okay? So, matching the coefficients gives the following. Minus 2n plus 1 times the summation that we're interested in equals negative 2n plus 1 choose 3, okay? Well, the negatives, we can multiply by negative 1 on both sides and cancel out the negatives, so to speak. And now, 2n plus 1 choose 3, let's evaluate it explicitly, right? So we're going to get 2n plus 1 times 2n times 2n minus 1 divided by 3 factorial. Looking good, looking good. There's a 2 in the numerator and 3 factorial has a 2 in the denominator. 3 factorial cancelling with 2 is just going to leave us with 3, not 3 factorial. Nice. And the 2n plus 1, if we divide by 2n plus 1 on both sides, we get the following. This summation from m equals 1 to n is equal, sorry, I forgot to cancel the 2 there, right? That 2 cancelled with the 3 factorial. And we get the following, n times 2n minus 1 divided by 3. And that's precisely the answer we were looking for, right? So just to summarise what we did there, in case there's any confusion, we have a polynomial equal to 0, and we know its roots. So by the factorisation theorem, we can factor this polynomial into a product, right? We then found the x to the n minus 1 terms of this product, right? And this gave us two different ways of expressing the coefficient of the x to the n minus 1. But because the polynomial is equal, we can match coefficients. And then when we match coefficients, we get the summation we're interested in, and after a bit of nice cancellations, we find that the summation is equal to n times 2n minus 1 divided by 3, okay? And now we shall go to the next part. We're almost at the end of showing what the Basel problem results in, okay? So the next part is now, given 0 is less than sine theta is less than theta, which is less than tan theta, for theta being between 0 and pi on 2 strictly, show that cotangent squared theta is less than 1 over theta squared, which is less than 1 plus cotangent squared theta. This should be quite simple. Okay, so first of all, let's start with the fact that sine theta is less than theta, okay? If sine theta is less than theta, then 1 over sine theta is going to be bigger than 1 over theta, okay? And that's justified because they're both positive, so we don't need to worry about dividing by a negative in the inequality, and taking the reciprocals flips the inequality sign. And finally, let's just square both sides. So we get 1 over sine squared is greater than 1 over theta squared. But recall that 1 over sine squared is nothing but cosecant squared. Yes, it's cosecant squared. And cosecant squared is equal to 1 plus cotangent squared. It's a trigonometric identity. So we actually see that this thing is equal to 1 plus cotangent squared theta. So we have 1 plus cotangent squared theta is greater than 1 over theta squared, which is precisely the right-hand side of this inequality. Okay? So we've got the right-hand side done, and the left-hand side should work very much the same. So we have theta is less than tangent theta. That means 1 over theta is greater than 1 over tangent theta, which is cotangent theta by definition. And then squaring both sides gives us the left-hand side of this inequality. So gluing them together, we get that inequality. Bada bing, bada boom, we're done. Okay? Now we'll move to the final part of the problem, where we actually prove the Basel problem. Okay, so it should be quite clear that we're now going to take the summation of this inequality and let theta equal m pi divided by 2n plus 1, right, and use the previous facts that we've established. But before that, we just need to iron out one thing to be a bit more rigorous, right? So remember, this inequality only holds when theta is between pi and 2 and 0, right? So let's make sure that m pi divided by 2n plus 1 is definitely within those bounds, right? The left-hand side of theta being positive is clear because m and n are both positive, right? But now, let's see that m is less than or equal to n. So that means m divided by n is less than 1, right? And then multiplying the both sides by pi on 2, we get m pi divided by 2n is less than or equal to pi on 2, right? Now, if we bump the denominator up, by 1, then it's clearly strictly less than pi on 2, and hopefully that's clear. So it's all good, we can let theta equal this value, and it will be within those bounds, and therefore this inequality applies. So that's a good thing, right? So now, let's let theta equal m pi divided by 2n plus 1, right? We get cotangent squared of m pi 2n plus 1 is less than, okay, letting theta equal m pi on 2n plus 1, we're going to take the reciprocal of that fraction and square it. So we get 2n plus 1 squared divided by n squared pi squared, which is less than 1 plus cotangent squared of m pi on 2n plus 1, okay? So we just let theta equal m pi on 2n plus 1 there. Now we're going to take the sum from m equals 1 to n on both throughout the inequality, and that should feel justified. That should feel like a justifiable step, right? If we have an inequality and it always holds true, then we should be able to take a summation over those terms, and the summations should still obey the order of the inequality. So I'm going to shove this inequality in. M equals 1 to n is less than. That is the world's worst sigma sign. Okay, so now we have three summations obeying the exact same ordering. But we know that the summation from 1 to n of Cm, which is precisely this thing, we just define Cm to be that for brevity, it equals n times 2n minus 1 divided by 3. So we get precisely that, right? So this entire thing breaks down very nicely. This, in fact, I'm going to erase this part. Okay, so this thing becomes 2n minus 1 times n divided by 3, okay? And similarly, this part's also going to become that. And finally, the little bit we need to deal with is we have a sum going from m equals 1 to n of 1. That means we're adding 1 n times. We're just going to get the number n. As such. And now, pi squared and 2n plus 1 squared are constants with respect to the summation because they're not being indexed over. The only thing being indexed over is m. So we can pull them out of the summation, and then we're going to multiply by its reciprocal to get it onto the other sides, right? So doing that, we get pi squared n, 2n minus 1, divided by 3 times 2n plus 1 squared is less than m equals what? The sum from m equals 1 to n of 1 over m squared, which is less than pi squared n on 2n plus 1 squared plus pi squared n 2n minus 1 over 3 2n plus 1 squared. Sorry, but all we did there was multiply by pi squared and then divide through by 2n plus 1 squared, right? And this is looking absolutely perfect because we've now got the finite sum from 1 to n of 1 over m squared. So we're getting really close to the Basel problem, okay? And now we're going to use our friend called the squeeze theorem, or also called the sandwich theorem in some countries. But basically, it says that we're going to take the limit as n approaches infinity of this inequality. And if the left-hand side of the inequality equals the same limit as the right-hand side of the inequality, then the middle is like sandwiched or like squeezed between those two things. And therefore it also equals those values as the limit approaches infinity, which is really nice. So taking the limit as n approaches infinity, I could be very formal and rigorous about this, but I'm not going to because it's already a long video. We're just going to look at the highest power on both the numerator and the denominator, and we're going to see what parts tend to 0 and what parts tend to constants, okay? So the numerator here has the highest order term of 2n squared, right? Sorry, times pi squared. So 2n squared pi squared. And the bottom is going to have a 4n squared times 3, right? Which is going to be 12n squared, okay? In the limit, n squareds are going to cancel and everything else is irrelevant because they're the highest order terms. So we're going to get 2 pi squared divided by 12, which is pi squared on 6. Looking really good, right? So as n approaches infinity, this left-hand side approaches pi squared on 6. This summation is going to be m equals 1 to infinity, because n is approaching infinity, of 1 over m squared. And this thing here, we have a linear n term divided by a quadratic n term. So as n approaches infinity, the denominator is going to beat the linear term, and it's going to become 0. And then this thing is exactly this thing, so it's also going to tend to the same limit. Okay? So we have this inequality, we let n approach infinity, and we find that the left-hand side and the right-hand side not only both tend to a limit, but they tend to the same limit, which is pi squared on 6. And therefore, via the squeeze theorem, we find that this infinite sum of the reciprocals of squares is equal to pi squared on 6. That went flying. And that is a solution to the Basel problem. Really interesting result. It's not clear why pi shows up here on the get-go, but as we can see as we go through the proof, we heavily rely on complex numbers in trigonometry, where pi is a regular suspect in those fields. So yeah, I hope you enjoyed the video. I think this is a pretty cool proof. It doesn't require any crazy facts or theorems. I think it's all pretty standard complex numbers and algebra facts, which we should all know and love. So yeah, see you next time.